fit test. This is a chi-square test, and the chi-square statistic can be used to determine how well a frequency distribution that we are given of observed values fits a specific pattern or distribution. These are what we expect to find. There are some requirements to use the goodness of fit test. Data must be obtained from a random sample, and we need the expected frequency in each category to be at least 5. When we do this, we'll calculate the test statistic. It's the same that we've been using before. Chi-squared is the sum of the difference in the observed values. We'll square that and divide it by the expected values. Again, since this is a chi-squared test, this will always be right-tailed. And basically what we're looking for, the important part here, comes down to this observed minus the expected. So if the observed values and expected values are close together, then the values of chi-squared will be small, because if they're very close, we'll be getting closer to 0. And that will mean, since it's a right-tailed test, that the probability will be large. Alternatively, if the observed values and the expected values are far apart, then chi-squared will be large, and this will lead to a probability that will be small. So remember what chi-squared looks like so. And if it's a right-tailed test, if the values of the expected and observed values are close, we'll get a chi-squared down here, and the right-tailed probability then is going to be very large. As opposed to if we have expected values and observed values that are far apart, then chi-squared will be out here, and the associated probability to the right will become smaller. There are degrees of freedom associated with the test. It is the number of categories minus 1. But the test works pretty much the same way. We're going to state the hypothesis and identify the claim. You'll have to find the critical value. Remember, the test is always right-tailed. We'll calculate the test statistic. Then we'll have to draw a conclusion, and we'll have to state it in some meaningful way using complete sentences that restate the claim. Now, how we state the null and alternative hypothesis is a little bit different. When there's two different situations. When we expect that the data in our n categories occur with the same frequency, then our null hypothesis will be that the probability associated with the first category is the same as the probability of the second, and etc., 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 down to the nth category. And then the null hypothesis will be that at least one of these proportions is different from the others. So it might be that p sub 0 does not equal p sub 1, or it could be that p sub 1 does not equal p sub 2. So at least one of these proportions will be different from the others. Now that's if we assume that the data in this n categories occur at the same frequency. But it could be that we might assume that the probabilities occur at some stated values. Then our null hypothesis will state, well, the first probability should have a value of 1, and the second probability should have a value of 2, and you keep going until your nth category, and you give it the nth value. Then the alternative hypothesis will again say that at least one of the proportions is not equal, now not to each other, but to the above stated value. So to do this by hand, we'll be actually just using our calculator. We'll be looking at how to do it in Excel as well. So just to become familiar with this process, both for the TI-83 and the TI-84 Plus. Okay, so let's do an example. Let's say a market analyst wants to determine whether customers have a preference of flavors among gelato. A simple random sample of 100 consumers were asked, what is your favorite flavor of gelato? And below is the data. Now, if consumers have no preference of a flavor, what would the expected values be for the data? Well, if there's no preference, then we would expect that each of these would occur with the same frequency. So cherry would have 20, since there's 100 and there's 5 categories. We're dividing everything 100 by 5, and we would get 20. So the claim is that at least one proportion is different from the others. This is going to be our alternative hypothesis. So we'll just say at least one proportion is different. Is different. Is different from the others. Okay. Now the null hypothesis, which contains the equality, would be that p sub 1 is equal to p sub 2, which is equal to p sub 3. We have 5 categories, p sub 4 and p sub 5. Okay, but then we'll move on. Let's state the level of significance for the test. We were told to do this at a 5% significant level. Or no, we were not told, I'm sorry. This was not stated in the problem. So we are making the assumption then that we can use the 5% significance level. Okay, for chi-squared test, it's right-tailed. This is always for chi-squared. Okay, so now we need to draw our diagram. Here's our chi-squared distribution. It's a right-tailed test at 5%. So in here, we're looking for 5%. And that means we'll be looking for, using our table, chi-squared at 0.05. To the right, we need to know the degrees of freedom. The degrees of freedom are the categories minus 1. We have 5 categories minus 1. So our degrees of freedom is 4. So if you look up on our table chi-squared of 0.05 with the degrees of freedom of 4, we get chi-squared is equal to 9.488. To find the test statistic, we're going to use our calculator. So from our calculator, if you follow those steps that were on the other page, into L1, we'll put the observed values 31, 28, 16, 14, and 10. And into L2, we had put the expected values, and these are all 20. And then into L3, we want L3 to calculate for us. We're going to take the observed, which is in L1, subtract off the expected, which is into L2, square that, and then divide by the expected, which is again in L2. Now when you do this, this is going to calculate L3, and you should get 7.2, 3.2, 0.8, 1.8, and 5. Now, to find chi-squared is going to be the sum of what's happening in L3. So you can access this again, the sum function, through the list in the math menu. And when you do that, the sum of L3 is equal to 18. Okay, so that's our chi-squared. Oh, we should probably put it in there. And I think it's pretty clear again, this is well into the rejection region. So just using the statistic method, the test statistic and critical value method, we will be rejecting the null hypothesis. But we can also do it with the probabilities. So let's go to the next page. We can find the p-value of the test statistic. For that, we'll use our chi-squared CDF. We start at 18 and we go to infinity. And we have 4 degrees of freedom. And you should get 0.0012. And so either way, what we will be doing is that we will be rejecting the null hypothesis, either based upon the p-value of 0.0012, which is less than alpha of 0.05, or because our test statistic 18 is greater than our critical value, which is 9.488, it is inside the rejection region. And after that, we can just translate the conclusion into our formal sentence. So at the 5% significance level, there is sufficient evidence to support the claim that the consumers have a preference among flavors of gelato.